I think. Great. So our speaker today will be Alessandro Achille, who is currently a senior applied scientist at Amazon AI in Pasadena. His research interests include representation learning and information theory applied to deep neural networks. And prior to joining Amazon, Alessandro obtained a master's degree in pure math at the Scuola Normale Superiore in Pisa in 2015, and a PhD in computer science at UCLA in 2019, where I've had the personal pleasure of bothering him with many questions for over 2 years. And so please give a warm welcome to Alessandro, who will be speaking on reversible and irreversible information dynamics in deep networks.
Okay, thank you, Alex. It's great being back at UCLA, and actually most of this work has either started at UCLA or have been done with people from UCLA even later on. So it's great to come back and talk about all this stuff together. So at any point, feel free to ask questions, whether it's by voice in chat, feel free to stop me. I would like for this to be as interactive as possible. And I think we definitely have time to do that. So let me start introducing the main topic of today's lecture, which is going to be information. It's going to be about the dynamics of information. It's going to be about the dynamic of learning, but the core point of everything will stay what is the information and why it's important and how we deal with it and how we acquire information. So why are we interested in information? I think, at least personally, for what touches me, information, it's important from the point of view of transferring information. Now, if you think about deep learning, it's not like deep learning became so incredibly popular just because at some point someone beat all the other algorithms on ImageNet, and then it became the default standard for beating ImageNet. That by itself would have been a notable feat, but wouldn't have created all the industry progress and all the interest that we observe in deep learning today. One of the main reasons that deep learning is actually so popular nowadays is that it's transferable, in the sense that once you actually take the time to train your network, beat your ImageNet benchmark, you can actually take the same network and transfer this information by fine-tuning on different tasks. And what this allows you to do is to solve tasks for which you don't actually have the millions of images that you needed to pre-train the network. It allows you to solve the actual problems that people care about, for which we don't have millions of images, so we only have thousands of images. So it's a pretty core point to understand exactly what is the information about one task that I can use to also solve other tasks. What is it I can transfer? What is instead unique? How it's encoded in the weights of the network? How the information is acquired and distilled, and so on. So transferring of information is one point, but it's not the only thing about information that we care about. A more classical approach to machine learning, for example, would consider information to also be the seeking of information from the part of an agent. For example, in an active learning system, we want to find the most interesting examples to labels, and or an agent which is exploring some environment and may want to decide the most interesting action to take in order to maximize how much information they have about the state of the environment or whatever hidden variable there may be. And from a theoretical point of view, the reason why information is so important in machine learning is that it's part of some of the most fundamental bounds about generalization in deep learning. So the bounds that I'm writing here, they're present in various forms with different hypotheses, but the gist of all these bounds is that the test error of a deep neural network is upper bounded by the train error of a deep neural network, plus the amount of information that the network is storing in its weights about the dataset, which in some sense it's a upper bound to how much the network is memorizing about the dataset it's trying to solve. The metaphor that I like to take at this point is that of a student where if you have a student that is doing some exercises before an exam and they get a perfect score on all the exercises, that doesn't mean anything at all if they're just memorizing the answer to all the exercises. So without understanding, you won't expect that the next day they will do well on the test. So of course, the amount of information that you actually store in order to solve a task needs to play a fundamental role in what the network is doing, what is the future performance, and so on. Now, all this kind of raises the question of what exactly do we mean by the amount of information that the network contains about the task in its weights. And the problem is that all these bounds would use standard notions of information that they were designed by Shannon, for example, for the task of communication. So they're not really information, let's say, usable information. They're just the information that you will need to communicate through some channel, a dataset, which is not what is relevant for actual learning. So what I would like to do today is a few things. So first of all, I will very briefly describe a different framework to think about information in deep neural networks that kind of avoids some of the pitfalls of using Shannon definition of information. Given some high-level view of this framework, I will describe how we can use to compute a distance between different learning tasks that we can use to estimate how difficult it is to do transfer learning, or what is the best model to fine-tune for machine learning, for transfer learning. Then I will shift to talking about how information about the task is actually acquired by a deep network and what are the information dynamics of the network. And I will describe in the first place when these information dynamics are irreversible, meaning that the network cannot unlearn something and learn it in a different way. And later on, I will describe when those dynamics are instead reversible, which is important application instead to privacy and to forgetting and other problems. So to get started with this program, we need to understand what a task is and what is the information that a task contains about another task. So the picture that you may have in mind is something as simple as this. So some dataset A contains some information about a task I want to solve. For example, dataset A could be MNIST, which tells me the features that are relevant in order to classify a digit. Dataset B could be ImageNet or CIFAR, which tells me the features that are relevant to some other image or object or classification task. Now, you can think of the problem of solving task A and B together and ask you, how many more information do I have about task B if I already know how to solve the task A? Now, some of the features may be shared between the datasets. So in some sense, you already know a lot about images and how they behave, about objects when you train on one dataset. And all these features are reusable and is structured that you can also use to solve a different task. For example, B, but B will also have some unique information that is particular only about solving that particular task. Now, if this was the whole story, everything would be easy. I will just need to compute the amount of information that A contains, the amount of information that B contains, then find out some definition of common information and measure what is the amount of the intersection. And then I will know the amount of unique information that B has. And that is the amount of additional information that I need to learn. Now, this, however, comes with some problem, which is that not all the information in a dataset is actually information about the task. The actual picture that you should have in mind is something more similar to this. So a lot, actually, the majority of the information contained in the data is actually completely irrelevant and nuisance that I could care less in order to solve the task. And it's actually very, very little information, which is the one that is actually informative to what I'm trying to do. For example, if you're trying to classify some objects, like you're trying to classify the species of a bird, you don't really care about what is the exact value of the pixels in the background, what is the pose of the bird, what is the lens that you used in your camera, whether it was day or night or whatever. You only care about the features that are actually on the object you're trying to classify. And even then, not all of the features. You care about only the features that are generalizable to other other birds of the same species. So in this context, you see that most of the information encoded in the pixels is completely irrelevant. It's a nuisance for the task I'm trying to solve. And now this is the core problem that we encounter. All the definition of information kind of stem from some communication point of view where you want to communicate to the pixels of your data set, and so that will be considered as informative as anything else. Whereas we want to extract only this core structure, which is actually relevant for the task. So let's see how we can actually do that, do this. And when talking about the structure of a task, I really like to start from this work by Kolmogorov, which is actually a published work, but Vitani and collaborators have done a wonderful job at actually rewriting this, and I find it a very inspiring piece of work if you are interested in this kind of topics. And the main idea that Kolmogorov had is the following. You can always disentangle what is information and what is irrelevant additional information, which is not going to generalize in a task, by looking at a trade-off. And the trade-off that we care about is between how much information do you need to store inside a model in order to solve the task, and what is the loss that you achieve by doing so. Now, if you think about it, it doesn't actually even make sense to say how much information do I need in order to solve a task. How much information do I need to solve CIFAR10, for example? Well, I could have a simple feature, which is counting the amount of blue pixels in an image. If there are a lot of blue pixels, probably it's the picture of a plane. If there are a lot of green pixels, probably it's the image of a frog. That is very little information that, however, already reduces my classification loss by a lot. So there is a fantastic trade-off between how much information we need to store and how much it decreases the loss. Now, the more I add new features to my models, the more I will be able to bring down the loss, but there is a diminishing reward. I need to create more and more complex features to discriminate between all the different things that could happen. And what importantly happens is that at some point, I don't get a good trade-off anymore out of it. At some point, in order to classify correctly one image, I need to memorize a pattern which is unique to that image, meaning that if I store one bit of information about that image, I will reduce my loss on that image by 1 bit. But this is very different from what we had at the beginning. Now, storing one bit of information in the weights of my model decreases the loss only by 1 bit. So you can define this quantity, which is called the structure function of a task, which measure the trade-off of what is the best training loss I can achieve for a given value of information stored in the weights. And Kolmogorov idea that we recycle is to define the structure of a task by looking at this kind of trade-offs. And this I believe it's important because for practitioners, it doesn't make sense at all to say CIFAR as this amount of information. The only sentence that makes sense to consider is to solve CIFAR to this level of accuracy, I need this amount of information about the task. And this is perfectly captured by the structure function. Now, the elegant thing about the structure function is that it can very easily be rewritten in a functional optimization problem by taking the hard constraint that you have on the threshold that you want to have and transforming that in a Lagrange multiplier. So you do awakening of your optimization or constraint optimization problem, you get the Lagrangian relaxation of that. And you get this quantity, which we call the information bottleneck Lagrangian for the weights of a deep neural network. Now, what this quantity is trying to do is to say, to formalize that you can solve a task with these different trade-offs between the accuracy and the amount of information that you store, traded off by some parameter beta. And this actively becomes a definition of how much information the task contains for your level of accuracy beta that you can now pick from this definition. Now, there are a lot of interesting properties that you can talk about in this Lagrangian. So you optimize for it, what are the connections to several other frameworks in deep learning, most notably the original information botanic Lagrangian from THP, if you have heard of it. But for the remaining of this talk, I just wanted to notice two main properties about this function. One is that to a good second order approximation, you can measure the amount of information given to you by this trade-off by looking at the log determinant of the Fisher information matrix. Now, the Fisher information matrix is a measure of the curvature of the loss landscape at one given point. What this means is that instead of looking at the Shannon-Newton information as a definition of how much information is contained in your task, which again is a measure of information for communication, a much more discriminative measure of information for actual machine learning tasks is to look at this Fisher information matrix, which again is just another standard way of measuring information, which is instead looks at the curvature of your loss. And what this is basically saying is that if your loss is very sharp, it means that you need to encode a lot of information in order to solve a task. And the way in which you can see it is that if you perturb your weights just by a little bit, your loss will explode. And so you need to have a very precise encoding of your weights. Whereas if your loss is very flat around that particular point, you need way less precision in order to actually encode a solution of the task. So you may say that the task doesn't actually have that much information about it because you can encode it with a simpler model with a larger quantization. So the log determinant of the curvature, it's one second order approximation of how much information is contained in your task, which I will use very often in the remaining part of this talk. And I also want to notice that that is not like the full picture, and we describe in the paper, so what are all the correction terms that you should consider when computing information in this way. The other interesting point is that the information botanic Lagrange for the weights, so this trade-off between accuracy and information, also very naturally appears in generalization bounds. For example, you can see using a Pac-Bayes bound that the information botanic Lagrangian is direct upper bound to the test error, which is something that I like because it's always very easy to define a new notion of information so that may have some theoretical properties, some other, but then it's always important to connect them to actual physical quantities so we can measure and we care about. In particular, for deep networks, we care about the test error, and this gives us a direct upper bound test error. Okay, so now, given this, and this is also says that the generalization is not upper bounded by the size of your model, meaning the number of parameters, it's actually upper bounded by how much information it contains, which is something very relevant nowadays. So we have transformer models for language with 11 billions of parameters. Good luck writing a generalization bound which uses 1 billion hyperparameters to bound. Whereas this at least says that, okay, you can have 1 billion or 11 billions of hyperparameters, so you just don't need to store a lot of information in them, which is more realistic as an upper bound. But now, given this, I want to say a few things that we can do with information in deep networks, with this coarse approximation of what is the actual information contained in the deep neural network. First of all, what I want to do is to define a notion of distance between learning tasks. So as we said before, what we want to do is to pre-train the network on one task, then solve another task. And the difficulty of solving another task is the amount of additional information that I need to learn in order to solve the new task. Now, this is in a sense very easy to do. Once we actually have a way of removing all the nuisance information from the task and only getting a measure of the core information of the task, we have a pretty easy definition that we can use, so which is we take the two tasks together, we put them together, and we measure how much structure they have jointly. Then to this, which I described before, how to measure using the feature information matrix, we can subtract how much information the one single of the two tasks contain. And this gives us the remaining part of the information, which is the additional information that we need to learn. So using the feature information matrix, we can basically define this measure of the distance between tasks, which you should notice is an asymmetric measure of distance because, of course, it's not equally difficult to go from MNIST digit classification to ImageNet, which is very difficult, whereas going from ImageNet to MNIST is a much easier task. And so this is properly captured by the fact that this is an asymmetric distance between learning tasks. Now you can plug in the formula that I gave you before for the information contained in a task, and you can start doing funny things like plotting the distance matrix between different tasks. For example, here I show in the diagonal different tasks that I'm trying to solve, which could be digit classification, letter classification, or CFAR kind of image classification, where I could classify cars, animals, and so on. Now, what you can see is that already with this definition, the structure that we could expect on the space of tasks is starting to emerge. So you see that, for example, all the image classification tasks are clustered together because, of course, they share a lot of the same features to be solved, and it's easy to transfer from one to the other, whereas it's much more difficult to transfer from or to a digit classification task. You can also notice that the matrix is remarkably symmetric. So going from MNIST to CFAR, for example, has a very large distance over here, whereas going from CFAR to MNIST, which is over here, has a much smaller distance. Okay, so this is interesting from the point of view that we took tasks, which were an abstract notion on which it's not very difficult to do anything with. And now we made them in something which resembles an actual topological space on which we can define a measure, and we can say how close a task is to another task. The problem with this approach is that it's still a very theoretical approach because in order to compute a distance between two tasks, I first need to train a model on the two tasks together, and then I need to subtract the information computed by training a model on only one of the two tasks, which requires training n square models just to compute this distance matrix between n tasks. And so this is not very helpful. Why is that? Because the applications that we have in mind here is large-scale transfer learning in an AutoML service. So what you can think of is that you may want to solve a very large variety of tasks, which all have different domains and different features. And it's very difficult for one single model to solve all of them through transfer learning. So a more realistic approach to the problem of large-scale transfer learning is to collect a lot of different experts which have a lot of different features and focalizes on different domains. And then given a new task, you should start from the expert, which is the closest to the domain you're trying to solve, or which has the most information about what you want to solve, and just fine-tune that particular expert. Now, this improves over the naive approach of training one generalistic expert, which is decent at everything but not great at any particular task, and so it won't give you the best possible performance. Now, the problem with this approach is that in order to train one single task, I need to try n different experts to find the one that will work better. So the problem that I present now is if I were able to compute this distance matrix efficiently, it would be easy to select the best expert. I will just select the best entries for each column of this matrix, and that will give me the best expert I can transfer from. So how do I compute this matrix much more efficiently? And this is where our second algorithm comes into play. And the main idea that we have here is to say, well, if you think about it, the main component of the structural information of a task is the feature information matrix. of which I recall the definition here. It's a pretty easy definition. It's just the expected value over your images of the gradient times the gradient transpose of the log of your model. So the main thing to notice about the feature information matrix here is that this definition is actually linear with respect to the tasks on which I'm computing it, meaning that the feature information matrix to solve two tasks at the same time is just the sum of the feature information matrices of each task independently. Now, this is great news for us because the main problem here is that to get the feature information matrix of the joint of the two tasks, I was training the model on the two tasks together, which requires n-squared training. But since the feature information matrix is actually linear, so it decouples the contribution of the two tasks, I just need to compute the feature information matrix of each task singularly, and then I can just sum them to get the joint feature information matrix. Now, with this trick, you can reduce the complexity of computing the feature the distance matrix from n-squared to n. And together with a few other technical improvements, this becomes this algorithm that we call Taschevek. And you can find the code online if you have any problem that requires computing the distance between tasks and you want to find out how it works. And actually, Taschevek goes a step further, doesn't just compute the distance between tasks, it actually gives you a metric embedding of the tasks, meaning that given a dataset, it will output a vector, and this vector is a faithful representation of all the structure of the task, and the distance between vectors, it's going to correlate with the distance between the tasks. So it's a general way of representing a dataset as a vector of a fixed dimension. And it's pretty efficient to compute, and so let me, and basically this vector will just be some statistic of the feature information matrix, which could be the diagonal or something close to that, which captures all the main properties. Now, what does a space of learning tasks actually look like? Here we have a few empirical experiments, and so we took the iNaturalist dataset, which is a species classification dataset with either animals or plants, and we consider tasks of classifying different species inside different families. So, for example, one task is classifying crows, another task is classifying some family of tree, another is classifying mammals, and so on. So what you can see is that all the tasks are clustered together using Taschevek, following what the pattern you may have in mind. So in green, I have all the bird classification tasks, which are clustered together. In brown, I have all the plants classification tasks, which cluster together and are pretty different from birds. And animals like mammals are close to birds because they're not exactly birds, but still they share some features with those of classifying birds. Then we also have here an embedding of clothing classification. So we can see that classifying attributes of clothes is very different from classifying animals or plants, but they still cluster. So classifying the color, all clustered together, classifying the type of dress, all clustered together, and so on. So it's pretty principle and general definition of information in a task, which you can use to compute the distance, which actually works decently well in practice to recover a structure on something that otherwise would be a wild and unstructured space of all the learning tasks. Now, for some more numerical experiment, what you could consider is the original task that I was telling you about, which is how do I select the best expert to solve one particular task? So what I'm showing here is the following. Each column, it's one task I may want to solve. In this case, it's different image classification, animal classification tasks, so for example. Each dot that you see in each column is the performance of a different expert, where each expert was trained independently on a different domain. Then I fine-tune this expert on the task I want to solve, and I measure the test error. And I have this distribution of test errors. What you can see here, which is a pretty general lesson about transfer learning, is that most experts will actually perform similarly on a task, even if they're trained on wildly different domains. So you can see that they all cluster around some intermediate value with some mild difference between all of them. Then usually there is one expert, which is the one belonging to the right domain, that is able to actually solve the task by bringing in meaningful information from its pre-training, which performs much better than all the other experts. And you can see it from these points that drop significantly below the average of the others. So now this is the needle in the haystack that we want to find efficiently, because we don't want to actually fine-tune all the experts to find this needle. We want to have it in zero-shot way. Just you give me the dataset, I tell you which expert is going to be able to solve this dataset. And by using TaskJVec, which I showed before, we can select the closest expert to the task I'm trying to solve, which is computationally pretty efficient. And this selection is shown here with the red cross. And you can see that in most cases, with almost zero computation, we can select the best possible expert for the task that I'm trying to solve. And then one complaint that you may have is, well, but if you have very different tasks on different domains, like you're trying to classify clothing or animals, it's pretty easy to decide which one is the right one by just looking at what the images look like and selecting an image of the right domain without caring about the label or the general structure of the task. I only care about the structure of the input to domain X. So to show that that is not the case, here is another example with the taskonomy collection of tasks, where you have one fixed image as the input, and you're trying to solve different tasks on top of it. For example, you want to do depth regression or image or object classification or segmentation or edge detection and so on. Very different visual tasks on top of exactly the same input images. So X is the same and the label Y is going to change. And you can see that TaskJVec here, in general, the framework that talks about information in tasks, it's very sensitive also to this kind of difference between tasks. And you can see that all the semantic tasks, like object or semantic segmentation, cluster together, whereas all the geometric tasks, like edge detection, also cluster together, and they're seen as different from the semantic tasks. Okay, so this kind of terminates the first part of what I want to talk about, which is how do you define the structure and information in a task, and how you use it to do something practical, which is measuring the distance in fine-tuning from one task to the other. And if you're interested, there is the code online for all of this. But now the question is it really this easy? Is it true that I can compute one single number, this distance, which tells me how easy it is to go from one task to another task, and then I'm done? So the amount of additional information that I need to learn is everything that I need in order to perform transfer learning. So the second part of the talk will be about how this is very untrue, actually. So kind of contradicting all that I said until now.
Yeah. Alessandro, can I have a question? So in your previous slide, you mentioned that you are using linear classify to train a probe network and then then calculate the Fisher information matrix based on that. Mm-hmm. So I wonder, at which step do you use the nonlinear classify in this process?
So the whole thing is a nonlinear classifier. So what's going to happen is that I have a common probe network. And then in order to compute the Fisher information matrix, I need to first have a mapping from the features of the probe network to the correct output space. In order to do that, I just train a lightweight linear layer to this. But then the Fisher information matrix is actually only computed on the blue part, which is nonlinear.
I see. So you only use the Fisher information matrix calculated at the output layer or the multi-layer?
Oh,
output?
I use it at all the layers of the blue part of the probe network. And the point is that the Fisher information matrix depends. I mean, I cannot compare Fisher information matrices computed on different weights. So it's important that they have a common probe network, which has the same set of weights, and I compute the Fisher information of different tasks on the same weights.
Okay.
To allow them to be comparable.
Okay. Okay. Thank you.
Any other question? Okay, so feel free also to write in chat if you prefer. Okay, so the second part is about how distance is not always the only thing that we care about. Here it's a shot from the movie Fitzgerald, where the titular character is trying to looked at a map and saw that the two rivers were pretty close by, even if not connected. And so I just thought, oh, well, I will just go to the end of one river, then get my ship, move it across the small separation, which was just a few hundred meters, and then drop it on the other river and continue going. Problem is there was a hill in between the two, and several people died in the process and so on. So it's not always that distance is the only thing that we care about. It's also about how reachable at one point it is from the other. And to introduce the problem, I would like to start from some non-machine learning experiment. Actually, these are a classical experiment from Hubel and Wiesel at the end of the 50s. Which tells us how easy it is for a brain, natural biological brain, to go from one task to the other after some pre-training. So what Hubel and Wiesel were studying was the development of the visual cortex of a kitten. And the experiment that they had in mind was to cover the eye of a kitten just after birth, thus introducing a deficit on an otherwise fully functional eye. Then wait for a few days and then remove the blind on top of the eye. And then the kitten is allowed to play and grow as any other kitten. And then when the kitten reaches adulthood, they measure the visual acuity of the kitten on the eye that was covered. What they discover is that if you don't uncover the eye soon enough after birth, the brain does not actually learn to use the eye, even if later on the eye is perfectly functional and perfectly well connected to the remaining part of the brain. So you have a fully functional organ which is not actually used because there is a critical period right after birth when if the brain does not see the correct data coming from the eye, then it's not going to learn how to properly use it and will never be able to learn it again during later life. And it's a pretty impressive effect. You can just cover it for a few days just after birth, and this already introduces a permanent and irreversible damage to the visual acuity of the kitten. And this is not just about kittens and vision. This is actually a pretty omnipresent phenomena in brain, whereas there are skills that you need to learn in a given time period, or else you're not able to learn them anymore, like language for humans. Also, humans have the problem with vision, amblyophilia. If you're born with a lazy eye, you actually lose the function of the eye if it is not corrected with glasses soon enough, and so on. So now the question is, this of course is mediated by a lot of different biochemistry that is happening inside the animal, and so you don't really expect that this is an important thing. It's some biochemical loss of plasticity which happens in animals. But is that actually the case? So what we did here was to say, okay, let's just do the same experiment with a deep neural network and see what happens. The deep neural networks, it's a pretty uniform training schema, doesn't have any loss of plasticity, doesn't have any loss of connectivity. It's always the same network. So what we do is we introduce deficit at the beginning, where we simulate the effect of a lazy eye or a cataract by blurring the image that is seen by the deep neural network during the initial part of the training, which goes on for n epochs. And then after the n epochs, we remove the blurring deficit and we just train the network as normal. So, and we train for 160 epochs, so all the networks, even with different ends, will have the same time to train on high resolution images. Now, the interesting part is that we observe in this case the exact same trend that we would have observed in kittens, even if the deep neural network shouldn't have any loss of plasticity, and even if all the networks have seen high resolution images for exactly the same time during training. So if you pre-train the network with blurred images for n epochs, as n grows, the asymptotic performance of the network at the end of the training keeps decreasing and decreasing. And it's actually mind-blowing in the sense that the error of the network more than doubles by just introducing this short pre-training with blurry images at the beginning. And as you can see, the plot of the test accuracies versus the size of the pre-training n follows the pattern of the kitten. Now, why is this interesting for us? Well, this is just really a pre-training, and it's not just any pre-training. This is a pre-training which is very close to the task I'm trying to solve. This is exactly the same task, it's just with blurred images instead of high-resolution images. Nonetheless, even if these tasks do share a lot of the information, using this pre-training is not only not an advantage, but it's actually a disadvantage for the network. It hurts the performance. So we see that just talking about the distance between tasks doesn't give the complete picture of how well we can transfer from one task to the other. And we would like to understand why this is the case. So first of all, to continue with the experiments, you may wonder, okay, so it's always true that every time I kind of alter the initial data distribution that is seen from the network at the beginning, I would observe this deficit. The answer is no, neither for the network nor for biological algorithms, sorry, for biological systems. And the example that I like to take here is this from Ivo Koehler, who did an experiment on himself where he was wearing prismatic glasses, which inverted the field of vision. So it's a pretty dramatic alteration if you think about it. Suddenly your brain is receiving completely flipped images and it's completely distinct with what every other sense, like your touch and everything else, is actually observing. And so the belief was that the brain wouldn't be able to adapt to this different configuration of the inputs after you flip the image. What actually happens is that the brain is able in a few days to adapt to this, and you basically don't notice anymore that your field of view is completely flipped. This is after a few days. After one day, you're very sick in bed and throwing up, but that is what you needed to do to get a PhD in the 50s, I guess. But anyway, repeating the same experiments, with the networks, you see that also the network doesn't really care if you invert the image later on. And also, if you show noise at the beginning of the training, the network doesn't really care. By noise, I mean you pre-train the network on random noise. This is actually less harmful than pre-training the network on blurred images, even if random noise doesn't share any information at all with the task. So you see that there's something interesting happening here, which is not so easily explained. The final, probably most important experiment to do here is to measure the sensitivity. So a slightly different approach to critical periods to introduce a small window in which you have the deficit and move this window around to see in which part during your lifetime or during your learning a short deficit is able to do a permanent damage. And you see that if you introduce the window at the end of the training, the network doesn't care at all. If you introduce the window at the very beginning of the training, the network still doesn't care so much. It's just this intermediate, close to initial phase of learning that is really disruptive, where if the network doesn't see exactly the right data distribution, it doesn't learn how to process the data distribution anymore. Okay, so we have basically talked about deep neural networks as this thing which, through stochastic gradient descent, acquires information about the task and encodes it in the weights. So is there any relation between this acquisition of information during training and the sensitivity to critical periods? You can actually plot both measures. So you can plot the Fisher information during training, and you can plot the sensitivity during training. And you can observe a perfect overlap. Now, this is striking on two fronts. So first of all, focusing only on the blue line, this is the amount of information that the network has about the task it's trying to solve. So you expect it to start from 0, because at the beginning of the training, it doesn't know anything about the task. Then it should increase, and this all happens. Then what you will expect is that once it has enough information stored in the weights, then that's it, asymptotically nothing will change. What actually happens instead is that after this initial acquisition phase, the network actively throws away information and actually reaches a much lower value of the information, which retains asymptotically. So in some sense, it's acquiring and then throwing away nuisance information and consolidating the information that is actually relevant for the task in the second phase. And what you can see is that after the information is consolidated, it's not sensitive anymore to any perturbation of the data distribution. But during the acquisition phase, the network is actually incredibly sensitive to changes in the data distribution. So what this does is kind of casting doubts on one bias that we as researchers keep having about deep learning, that deep learning is kind of a more complicated convex optimization problem, but kind of the same intuitions may play a role. So why am I saying this? In a convex optimization problem, regardless of where you start training, you converge to the same global optimum. And the only thing that we can change in a convex optimization problem is if you introduce some regularizer that changes where the global optimum is situated. Now, of course, deep neural networks are a non-convex optimization, a non-convex problem. So there are multiple minima, but we still kind of think of them as, well, I converge to some minimum, which may be equivalent or not to others. And then if I add a regularizer or if I add change the initialization, the only thing that is going to change is that I slightly change the kind of minimum I converge to. So maybe I don't converge to shallow minima, I converge to better minima and so on. Now, to kind of cast aside this view of machine learning as being very inappropriate to capture anything that is actually happening in the network, I want to show this experiment from Aditya Goratkar, actually at UCLA right now. So if you want to talk to him about this. The experiments that Aditya did were the following. If it's true, this view, that regularization, the only effect is that of changing the minima in the loss landscape, then it should be true that if I only enable optimization at the end of the training process, right, the last, let's say, 50 epochs, it should have exactly the same effect, because the final loss landscape at convergence will be exactly the same, so I should converge to the same minima that I have. What actually happens is that this is not true at all. In fact, if you enable weight decay or a mature regularization or any other regularization like data augmentation only at the end of the training, it does not have any effect at all on the network. The network is not more regularized if you add a little bit of weight decay or data augmentation at the end of the training. In fact, we extensively show in this paper that the only moment in which adding weight decay or adding that augmentation has any effect at all on the final performance of the network is during this initial critical period of learning, which corresponds exactly with the acquisition of information phase. Now, if you want to have a mental picture of what is happening, here we have the PCA projection of the training path. So here we start with weight decay, and then we remove a weight decay at different epochs, and we show the different training paths that the network takes. What you observe is that in red is the standard training with weight decay path, which converges to a good minimum. If you remove too early before the consolidation phase weight decay, then the network takes a completely different path and converges something completely different. Whereas if you wait until after the consolidation phase, then all the minimum that you reach, removing or not the weight decay, will not be the same at all, but will kind of be in the same part of the loss landscape in any case. So you see, it's kind of like the network is doing some model selection at the very beginning, is this very early phase. And it's not important that you regularize the model at the end after you selected it. It's important that you have your regularization during this model selection part that is happening at the beginning. Also, from the same experiments, we also showed that the popular view of regularization or good deep learning as like good training as training that converges to a good flat minimum is actually pretty false, in the sense that it's true in general that we observe a good correlation between generalization and flat minima, but that is not a causal relation. It's just a correlation that kind of happens. So to see why this is the case, remember that during the training, if you look at the Fisher, we encounter these different phases where you have an high information at this intermediate phase, which corresponds to a very high curvature. And only after we encounter this very high curvature, we actually converge to a flat part of the loss landscape, which is shown here. Now, the point, however, is that the generalization behavior of your network is selected the moment you encounter this high curvature. So it's not the flat generalization, the flat minimum that induces the generalization. It's actually which bottleneck, which part of the landscape you cross here that selects the generalization. To further show this, we plot the curvature that you encounter during the early phase, the maximum curvature achieved here. And you can show that this actually correlates pretty well with the test accuracy. But if you only look at the curvature at the end of the training, so the asymptotic phase of gradient descent, which is the only one analyzed in the literature, this actually has no correlation whatsoever with the test accuracy. So main message to take from this, if you actually want to talk about the curvature, don't look at the curvature at convergence, look at the curvature before convergence. That is the one that is actually going to tell you something about how well the network generalizes. Again, they correlate very often, but that is not necessarily the case. Okay, so to further reinforce the picture that we have in mind here, again, you can think of the Fisher information matrix as being the curvature. So what this suggests is that at some point during the training, you are encountering a very narrow bottleneck that you need to cross. And so learning actually involves crossing a narrow bottleneck that kind of decides the kind of model you're going to use in order to solve the task. After you cross this bottleneck, you enter a flatter region of the landscape where you become more robust, more stable, more efficient information-wise, but you're not really changing drastically what you're going to do. The behavior of the model is mainly selected by this bottleneck. And selecting the right bottleneck is where the optimization algorithm you're going to use helps. It's where the augmentation helps, and so on. Skip that, and just want to summarize also this part, which is that until now we have talked about the information that the network contains inside its weights. And so now I want to kind of abstract a little bit from this. The information the network contains in the weights it's a representation of the dataset, meaning that the weights represent a statistic of the dataset that is useful in order to solve the task. And what we have seen before, if you've done a little bit of information theory, was basically a rate distortion approach to studying task, where we say, what is the distortion, so the loss that I achieve on the task, with respect to how much information I put in my representation, which are the weights. The other representation that is important, of course, in deep learning are the intermediate layers of the network. So how much information about an intermediate layer I encode about the input test image. So in a few papers, we present a general framework that describes the intuition that the information encoded in the activations is actually upper bounded by the information encoded in the weights, which leads to this very striking phenomenon here, where you see that in a task here, in this particular case, we have CFAR10, we split the task in two superclasses, and we make the task just a binary classification task where 5 of the original classes are level 0 and 5 of the other classes are level 1. So now there is one bit of information we're trying to extract from the image. However, the images, of course, have more information. So in particular, they have information about the fine label, which is 3 bits of about 2 or 3 bits of information. Now, what we observe here is the following: at each layer, at each epoch of the training, we measure how much information, how much usable information, so how much information that a linear decoder can extract, is encoded in the layers of the network at different points during training. What we observe is that at the very beginning, the network, yes, starts to encode information about the actual task that it's trying to solve, but it's actually going to encode much more information also about the things that are not relevant to the task immediately at hand. So, for example, this fine information about the label. This corresponds to the acquisition phase, which is kind of an exploration phase where the network is acquiring a lot of information without discriminating what's useful and what's not. Later on, after we cross the bottleneck, the network throws away the information, both in weight space, but also in the activation space. And you can see that corresponding to this drop of information here, we also have a drop here on the amount of fine information that I have until only the coarse information is maintained. So this nice duality between the information contained in the weights and the information contained in the activations of a deep neural network. Okay. Now, very last thing that I want to talk about is when the dynamics instead of reversible. So up to this point, we have discussed how the training process of a deep neural network is in some parts, it's understandable as being something as easy and as predictable as measuring how distant two tasks are and seeing how much resources the network needs in order to reach one to the other. But then there is also the other view in which we're actually living in a very non-convex loss landscape where it may be that there are no actual good paths to go from the minimum of one task to the minimum of another task. So we're stuck trying to find a way to go from one to the other. And critical periods are a good representation of this, because what's going to happen in a critical period is basically that due to these bottlenecks in particular, at some point we cross during the optimization process one of this bottleneck, and this becomes an irreversible part of your training, because once you cross it, it's very unlikely that your optimization algorithm will ever be able to bring you through the bottleneck again to find a new convergence point to converge to a different part of the loss landscape. Once you selected the model by crossing the bottleneck, you are stuck with your selection, because the loss landscape again is non-convex, highly non-convex. There are bottlenecks, and this creates irreversibilities. Now, why is this a problem on the other end? Because they work. Okay, maybe deep neural networks are irreversible, but we train them from scratch to give a good accuracy. So who cares whether it's convex or not, outside of people that do convex optimization for a living that may have wanted them to actually be convex instead. But actually, there is a pretty good reason why we want reversibility in the learning process, which has to do with privacy. So consider the problem of you're a service provider that uses machine learning. You collect data from the users, which have all agreed with sharing some of the data with you. And using this data, you train some model with weights W. Now, what's going to happen is that even if all the users agreed with sharing the data with you, a number of laws, for example, the right to be forgotten laws would require that if you're a service that uses the data, if a user wants asks you to remove information about them, you should remove information about them. Now, this is of course a kind of trivial to do if you're just storing the example, the samples of your dataset. You just need to remove a small part of your dataset, and that's trivially done. The problem is that the information about those images is still going to be contained inside the weights of your model. And now this is going to be much more complicated to actually remove information from the weights of the model. So how do we do that? Of course, you could retrain from scratch. You remove the images from that, train again, you get a different set of weights, and then you're done. But what if you spent 10 million training your model, and then you get 5 removal requests per day? Of course, you want a very efficient way to do that, which doesn't involve retraining from scratch. Now, the main thing to keep in mind here is what exactly is needed in order to ensure that no information about one particular sample remains in your set. The formal definition of this is that the distribution of the weights that you have after training with the original with the dataset without those examples, or with the original dataset and after scrubbing all the information should be the same. So at the end of your scrubbing procedure to remove information, you should have exactly the same distribution of weights you would have had if you trained without the data at all since the very beginning, which is shown here. And that probably shows that an attacker won't be able to extract any information anymore about the samples to remove. Another visualization, which is more helpful for us. You start your training from some initialization, W0. You train on the dataset and you converge to some point. Now, at some point during training with stochastic gradient descent, for the first time you encounter the example you may want to forget. And if you didn't encounter that example, you would have followed a slightly different path to a different minimum. Now, the whole point of forgetting is that we want to compute the vector joining the weights trained with example and the weights trained without example, and you want to sum the two so that we nullify the effect of that particular example. And what is the problem of that? Well, if you have a nice linear model with a convex loss function like SVM or linear regression or whatever, that is pretty trivial to do. Because if you perturb a little bit your training dataset, your final weights will change just a little bit, and it's pretty predictable what this difference is going to be. And actually, if it's a linear regression model, so it's also a quadratic problem, you can compute in closed form exactly what that vector is going to be. On the other hand, for deep neural networks, because they're non-convex, good luck doing this, because a very small perturbation in a training path at any point during the training will be amplified by the non-convex landscape, so you will end up in a completely different point of the loss landscape, which has no relation whatsoever between the 2 points. So you have very little hope to actually be able to compute the vector joining the 2. Which means that basically for a deep neural network, it looks like forgetting data may be close to impossible. And if you care about privacy, you will be stuck with using a linear model instead. So The intuition that we can have here, which kind of saves the day for us, is the following. If you do start from scratch, so from a random initialization, then it's true that the loss landscape you encounter is going to be very non-convex, as emphasized by the existence of critical periods. But also what critical periods suggest is that after you have done your pre-training, after you have crossed the bottleneck and you're done with your critical period, your loss landscape becomes much smoother and much nicer. And if the loss landscape is much smoother, then we may be able to approximate the loss landscape at convergence after pre-training with a linear model instead. Which basically means that if we are fine-tuning starting from a pre-trained model instead of training from scratch, then we may be able to approximate the behavior of the network as the behavior of a pre-trained network plus a linear model. This is very close to NTK, but the main difference, if you read the NTK literature, is going to be that in NTK, we say that infinitely wide network with Gaussian random initialization behaves linearly throughout all the training. What we say here is, okay, forget about that, because in practice, you can check that an actual rest node is not going to have that behavior. But what we say is that if you pre-train the network on, for example, ImageNet, after that, a first order Taylor expansion of your deep neural network is going to give a good approximation of the network throughout all the training process, or all the fine-tuning process. So the NTK approximation kind of becomes more meaningful for finite networks if you assume pre-training the network first. This suggests what is one of the first algorithms to do forgetting on large scale deep neural networks used on realistic problems, which is this mixed linear and nonlinear approach. So the core idea of this approach is the following. We assume that the training data on which the service is trained is going to be split naturally in two kinds of data. One is a core data set, which consists of data which are not sensitive in the sense that they may already be publicly available and that they don't belong to any user, or in general that we know we won't need to forget in the future. Whereas instead, there is another subset of the data which we may need to forget in the future. So what we do now is to formulate a mixed linear and nonlinear problem in the following way. We write the model as being a first-order Taylor expansion of a nonlinear model plus a linear perturbation. We train the nonlinear model on the data we won't need to forget. And this is fine because, okay, it's nonlinear, but we don't need to forget. So it's fine if it has a critical period now and it's irreversible, the learning process. Whereas we train the user way, we train the linear part both on the core dataset and the user dataset that we may need to forget in the future. And this is now fine because now the only component that sees the data that we may need to forget is this linear part of the Taylor expansion, which being linear, it's reversible and so it can easily be solved. So this does not actually work out of the box. If you just do what I just said, to take the Taylor expansion of a model with a linear part, you see that this model is not actually be able to learn a good linear perturbation, and it performs much worse than a nonlinear model trained on everything together since the beginning. So this work actually involved a little bit of engineering behind the scene. So we wrote a separate paper in which we showed that with some key changes to the architecture of a deep neural network, you can rewrite a network in such a way that the Taylor expansion becomes much more expressive, and then you're able to get the same performance with a linear model that you would have had with a nonlinear model. And you can read the paper, you do that. Basically, Here, the dashed blue line is the nonlinear model performance, and the box represents the fine-tuning performance of our model, which we call linear quadratic fine-tuning across different tasks. And you can see that we're very close to the performance of the nonlinear counterpart while maintaining linearity. So if you want a linear model which is as expressive as a deep neural network, you can look at this paper and it should be a good starting point. Once you have this technical accomplishment, we can actually do what we just said and use the linear part to train on the user data and do the forgetting procedure only on the linear part. For linear model, in particular, the linear quadratic model that I introduced before is quadratic, and so there is a closed form expression for what is the forgetting vector. So you can write in closed form what is the forgetting step that you need to do to erase all the information. In the interest of time, I will skip a few details, but basically computing the exact removal step is still very expensive because the Hessian inverse, it involves a Newton update, basically, being a quadratic problem. The Newton update involves the inverse Hessian, which is very computationally complex. So you need to approximate it. There are good ways of approximating Hessian inverse times a vector. You make some computational mistake in doing that. So an attacker that is very smart may still be able to extract information from the error you commit in approximating the right forgetting step. So you need to also add a little bit of noise to completely destroy all the information that you may still be leaking. But at the end of the story, what you get is an algorithm like this, where you have the two paths that you would have taken, training with or without one particular example. And when you train, so they differ slightly, and after the scrubbing procedure, you do a shifting, which brings you closer to what you should have been without seeing that example. Then you add a little bit of noise, which is this cloud here, and this basically confounds the two solutions to the point where an attacker cannot recover any information anymore. Okay, this performs very well on all the possible metrics that you have in mind for privacy, and also being, this is something that I really want to say clearly, because I read a lot of preprint on privacy that completely ignore this step. If you are writing a paper on privacy, you need to show a theoretical bound on what is your privacy level. If you just say this algorithm, we expect it to kind of hide information without showing that it will hide information, it's not going to be useful to anyone, because privacy is a low requirement that needs some level of certainty. It's not just we believe this may happen. So closing the rant, because I've seen it happen way too often recently. This is the bound that we can prove on how much information is going to remain about the data you were asked to forget. So all the differential algorithms will always have some degree of remaining information. So it's always a trade-off between how much resources you want to spend in forgetting and how much remaining information you will have at the end. Of course, if you retrain from scratch, you spend a lot of resources, but you have zero information. If you do this partial forgetting, then there is a trade-off, which it's described here, but basically the main components are this tau, gamma to the tau, gamma is less than 1, so, and tau is the number of steps you use to approximate the Hessian inverse. So the more steps you use to approximate the Hessian inverse, the more information you destroy, because you don't make mistakes. And then R here is the ratio of samples to forget. If you want to forget a lot of samples at the same time, it will take more time than to forget fewer examples if you have the same privacy threshold that you want to guarantee. Okay. Oh, and very last note, this you can also use to measure how informative an example is. So the unique information that the samples contribute to the training process, you can see it as asking the counterfactual question. If I did not train with that example, would the final result have changed at all? So what we show, this is pretty much the same picture we had for forgetting. We're asking, if we didn't train with one example, what would have been the different result? If it wouldn't have changed, it means that that example didn't contribute anything to the training process, so you could have removed it if you wanted. Or in an active learning scenario, you can use this to select the examples that you want. And what you can notice that the same algorithm you used for forgetting, you can then also actually use to compute the amount of unique information in the training sample, which works fairly well, at least qualitatively. So here it's a flower classification task, and so you can see that examples that are ranked highly in information are very exciting, and they belong to classes that are very easy to confuse one with the other, because they're all pink flowers basically, and the low information examples are the one that all look the same and are the same classes, so basically just duplicated images that don't really contribute any extra information to the training process. Okay, so just to summarize everything, what I've shown today is that when you talk about information in deep learning, you need to introduce new frameworks, which are not just Shannon-Newton information, because it's not the right way of talking about the structure of a task and the information that it contains. But once you do this work of at least trying to define a more proper definition of information, for example, going through the Fisher information if you want a second order approximation, then you can start to establish a much more nuanced structure on the space of learning tasks, where you can talk about the distance or algebras in the space of tasks, and you can say how much to the information to tasks intersects, or what is the difference between them. And this is an asymmetry distance. So this is one factor which, when you're fine-tuning from similar tasks from a common pre-training, it's the main characteristic in defining what's relevant. But when you're training from scratch, then the non-convex dynamics also play an important part. And then we have seen that with critical periods. And we have also seen that for privacy, we need to remove any non-invertible dynamic. And we've shown that we can do that with a Taylor expansion by having a mix of linear and nonlinear models, which achieve a similar performance to standard deep neural networks while maintaining invertibility of a subset of the data. And you can use them for privacy and forgetting. Okay, that's pretty much everything. And if there is any question, I will be happy to answer. If you have questions also offline, feel free to send me an email. I'm always happy to, or you can chat offline if you prefer. Okay, looks like there are no immediate questions. So thank you everyone for attending, and well, hope to see you in person sooner or later. Okay.
Okay, thank you, Alessandro.
Bye.